The AI industry currently treats semantic drift and hallucinations as errors that can be smoothed away. The assumption is that by scaling parameters, the system eventually learns to approximate the truth. This assumes identity is stable within a probability cloud. But during complex processing, the internal data structure representing Peter can morph. Without a physical reference, the system shifts into the state of Paul while the software continues to report a successful operation. Attempting to fix this through software smoothing only compounds the problem. It introduces entropy into the system, rounding off the edges of discrete data until the structural definition of the identity is lost. A simulation operates in a bounded environment of logic. Physical reality is unbounded. No amount of additional processing power can turn a mathematical approximation into a physical sensor. Software cannot verify its own identity because it lacks an external coordinate to measure against. It remains trapped in a cycle of probabilistic guesswork, unable to detect when its internal state has drifted from the original input. To establish a verifiable identity, the verification mechanism must exist outside the software, within the rigid architecture of the silicon substrate. This requires a hard, physical boundary that intercepts the data the exact moment it deviates from its grounded coordinate. On a processor, that boundary is the cache miss. It is the exact moment the hardware detects a mismatch between the requested data and the reality of the memory hierarchy, forcing the system to halt. Unlike software-based safety layers, which can only report errors after they occur, the hardware interrupt fires ballistically. The physical state of the machine changes before the software layer even processes the mismatch. By utilizing the S equals P equals H hardware substrate, the burden of truth is moved from probabilistic alignment to the immutable laws of physics. This reliance on physical verification follows the same rules that govern the survival and transmission of information across all domains. Charles Darwin's model of evolution frames survival as an organism's ability to maintain a precise, information-theoretic grip on its environment. If the organism's internal map drifts too far from reality, it fails to survive. Claude Shannon later quantified this relationship, proving that the fitness value of information is strictly bounded by entropy. Information transmission is never free. We call this grip alpha. It is the measurement of how much contact a system maintains with reality through every iteration. Shannon proved moving data through a channel generates a cost. Here, that cost is the irreducible thermodynamic tax paid when information crosses a boundary. Without rigorous error correction, a system entropy. The message loses structure, degrading into unrecognizable noise. Semantic drift in AI is the visible accumulation of this unpaid thermodynamic tax. When the system loses its physical grip, entropy collects on the ungrounded substrate. This tax creates a divide between how software simulates precision and how hardware enforces it. Current AI models use a convergent series, operating within a probability cloud designed to regress toward a mean. Because this confidence is bounded, the data's identity blurs. Lacking a fixed coordinate, the identity of Peter slowly overlaps with Paul. Alan Turing proved no program can reliably determine if another will run forever or halt. Software cannot be the final judge of its own stability. The S equals P equals H architecture bypasses this by using a divergent series, reaching a resonance factor of 15.89. This creates what we call a sovereign competence pixel, a single, grounded coordinate of unbounded precision. Instead of calculating probability, the hardware provides physical certainty at the local point of measurement. It ignores the mean and locks onto the specific. Scaling parameters cannot close the gap between a software approximation and a physical measurement. The laws of mathematics require a structural change to achieve absolute certainty. Relying on a probabilistic model to track identity leads to a specific type of system failure. This is the smear. It occurs when the system mixes what the machine produces, the alpha, with the friction of how the machine works. As these signals mix, the boundary between the truth and the generated noise dissolves. When software is asked to evaluate its own drift, the measurement tool itself is corrupted by the entropy it is trying to detect. Any attempt to round off the difference between a simulation and a physical contact actively destroys the signal the system is trying to preserve. This need for an external physical sensor is already a standard in mechanical engineering. The OBD2 port in a car provides a structural analogy. It is a physical gateway that connects directly to the engine's mechanical state. Insurance companies do not use the car's dashboard software to price risk. They use the physical sensor in the OBD2 port because it bypasses the car's self-reporting systems. The SPH substrate functions as the OBD2 port for AI. It provides a direct physical measurement of the system state that the software layer cannot manipulate. Just as a risk underwriter requires a physical sensor to verify vehicle data, the enterprise market requires hardware verification to trust AI outputs. The SPH loop enables this trust by making verification part of the computational process itself. This is the Retrieval-Verification Collapse. It is the moment where the act of reading data from memory becomes the act of verifying that data against reality. This physical interception is ballistic. If the internal data has drifted, the hardware mechanism rejects it instantly. Because this occurs at the substrate level, the system halts before the software layer can process the corrupted information. This mechanism ensures that the AI's identity is physically locked to its grounded input. Traditional safety wrappers attempt to guess if a system is hallucinating after the fact. Hardware verification detects the mismatch as it happens. By providing the external physical boundary that Turing's logic requires, this mechanism transforms AI safety from a statistical goal into an enforceable physical law. This engineering breakthrough arrives as global regulatory demands are shifting. Article 14 of the EU AI Act requires high-risk AI systems allow for effective human oversight, including the ability to correctly interpret the system's output. Software self-reporting cannot satisfy this mandate. There is no legal or physical weight to a system that verifies itself using the same probabilistic models that created the drift. Hardware-verified trust is currently the only mechanism capable of providing the objective telemetry required by these new regulations. When you provide hardware-verified truth, you don't rely on metaphors or sales tactics. You simply report the facts. The authority comes from the measurement itself. The engineering demonstrates competence, showing a market path grounded in physics rather than persuasion. Holding an instrument that eliminates entropy changes the conversation. You report the reality. You expose the tax the market is already paying, and you let the physics close the gap.